Thank you. This is Toru Takisaka from National Institute of Informatics. This is a joint research with Kitty von Farrakhan, Thomas Haas, and Ichiro Hasuo. In this talk, we introduce a novel technique of reachability analysis in stochastic games. Bounded value iteration is a technique to approximate reachability probability in stochastic games. A notable feature of bounded value iteration is that it can approximate reachability probability with precision guarantee. For example, bounded value iteration can answer a query such as compute reachability probability with 0.01% error range. Our contribution is to provide a faster algorithm compared to with the existing one. Faster computation is achieved by performing global propagation, which enables us to omit end component computation that is indispensable for existing algorithms. Let me first explain the problem setting. Our system model is a stochastic game, that is the probabilistic system controlled by two players, controller and adversary. The system evolves in discrete time and has finite states and actions. We are interested in the reachability objective, that is, there is a designated final state and we would like to know the probability of reaching it eventually. Let us see the following easy example, car versus pedestrian. A car is going to pass a crossroad, and there is a pedestrian near the crossroad. The controller, that is, the driver of a car, would like to pass the crossroad without hitting the adversary, that is, the pedestrian, no matter how the adversary behaves. This is a model of the situation by a stochastic game. The game is played in this way. Starting from an initial state, say pedestrian's action in this case, one of the players chooses their action. The active player at each state is determined by the specification. In this example, the adversary is the active player at the state pedestrian's action. Now there are two actions available at this state, stop and pass. The adversary chooses one of them and a transition is made accordingly. If the adversary chooses stop, then the car can safely pass the crossroad and we reach to the goal state. If the adversary chooses pass, then the car must do some evasive action. Such a situation is described by the car's action state, and now the controller chooses their action, brake or honk. The game is continued indefinitely in this way. For each player, their choice of action at their state is called a strategy, which is a map from the player's states to the action set. For example, one possible strategy for adversary is to choose pass at pedestrian's action, and one possible strategy for controller is to choose brake at car's action. Once the strategy of controller and adversary, say sigma and tau, are determined, we can define reachability probability under those strategies as a function from states to real numbers. That is, a function that receives a state S and returns the probability that goal is visited during the play, starting from S under sigma and tau. In the example, reachability probability under the aforementioned strategies has this value. Now our problem is to compute reachability probability under optimal strategy, that is, the function v defined in this way. This definition formalizes our intuition that controller and adversary would like to maximize and minimize reachability probability respectively. In this simple example, we can easily verify that the aforementioned strategies are optimal. But for more complex games, we look for an approximation technique which is computationally feasible. One of the well-known techniques for such a problem is value iteration, which is a fundamental technique in probabilistic model checking or machine learning. In value iteration, we compute an increasing sequence of lower bounds via an iterative computation. It is known that value iteration generates a converging sequence to the true value, but its shortcoming is that without an additional information, we do not know how tight the band is at each stage. Because of this, it cannot return a sound answer to a query which requires precision guarantee, such as compute reachability probability with 0.01% error range. Bounded value iteration is a variant of value iteration that addresses this problem. The idea is very simple. We also generate a decreasing sequence of upper bounds. By this, we can estimate the error range by taking the difference of upper and lower bounds. We can also return a sound answer to a query which requires a precision guarantee by continuing iteration until the error range reaches to the required precision. Notice that to guarantee termination of such an algorithm, we need to assure that both lower and upper bound converge to the true value. Okay, so now one might wonder that where is the room of technical contribution here? Isn't BVI and technique that merely performs value iteration twice in parallel? The answer is no, it's more than that. More concretely, we need some trick to assure convergence of upper bound. First, let's briefly recall how value iteration updates lower bound for simplicity at controller states. Value iteration alternatively iterates two procedures in the picture. First, based on the current lower bound, value iteration estimates an optimal action at each state according to the value L after a transition. The left picture illustrates that value iteration estimates that action 2 is optimal at the leftmost state. Second, based on the estimated action at each state, value iteration propagates the value of L along the transition arrow in an opposite way. The right picture illustrates that value iteration updates the value of L at the L leftmost state by backpropagating the value of L according to action 2. Through these procedures, a lower bound L is updated to a new lower bound. This operation is called Bellman update, and the operator that performs this operation is called Bellman operator. So in terms of Bellman operator, value iteration is a procedure that generates this sequence starting from some initial lower bound L0. Now the reason of non-convergence of upper bound can be explained in terms of fixed point. First, Bellman operator is monotone over the set of functions from state set to the unit interval with this constraint. Here, sync state is another designated state from which the final state is never reachable. The partial order of this set is given by the pointwise inequality. It is known that optimal reachability probability is the least fixed point of Bellman operator, that is, V equal mu x holes. Therefore, by clean a fixed point theorem, value iteration generates an increasing sequence of functions that converges to V starting from the bottom element as a canonical initial lower bound. On the other hand, if we start from the top element of the domain, which is a canonical upper bound, then value iteration generates a decreasing sequence that converges to the greatest fixed point of X, which may be strictly above V. In such a case, we have a non-convergence issue. Existing BVI algorithm resolves this issue in the following way. If the system is an MVP, that is, there is no adversary state, then the greatest fixed point can be matched with the least fixed point by merging end components. Roughly speaking, an end component is a part of an MVP that constitute loops. Non-convergence occurs at each state of end components because when we perform value iteration, an upper bound is only propagated inside the end component, and information from outside is cut off. It is well known that each end component can be merged into a single state without changing reachability probability. In such a modified system, the greatest fixed point matches with the least one, and the non-convergence issue does not occur. For an arbitrary stochastic game, more involved computation is required because some end components cannot be merged. Instead of that, we periodically perform a singular update over specific end components while running the standard value iteration. Such a singular update is called deflating because it reduces or deflates the value of upper bound over specific end components through propagation from outside. Now we will introduce our novel BVI algorithm. In the previous slide, we saw that every existing BVI algorithm involves end component computation, but it can be a bottleneck of execution time of BVI. It can be particularly influential in the BVI algorithm for stochastic games, where end component computation is required for each deflating procedure. Instead of computing end components, we try to ignore them. End component is problematic in value iteration because it performs local propagation. In other words, it chooses the value to propagate at each state by only looking at possible next states. Because of this, value iteration misjudges that staying at an end component is an optimal behavior. Instead, we globally propagate the value of an upper bound to each state along the path to the final state. In this way, we can naturally avoid being trapped into end components because we enforce the update procedure to define a strategy that tries to reach to the final state. In what follows, we explain how our algorithm works for an MDP, that is, a stochastic game that is played by controller only. After that, we explain how it is extended for the general setting. First, we need to specify the meaning of a path to the final state, and for each of them, the value to be propagated. To this end, we transform the given MDP and an upper bound into a weighted graph. As an example, let's consider the following MDP and an upper bound U. From this, we first construct a table as shown here. For each state and action available there, the table has an entry which consists of the state, the action, the value of U after a transition from the state under the action, and the set of possible next state. Now we construct a weighted graph in this way. For each entry of this table, we put the state in the first column as the source vertex. We put each state in the possible next state column as the target vertex. We put edges accordingly, and we put the value of U after a transition as the weight of edges. We do a similar thing for each entry of the table and construct a weighted graph. Next, we compute a new upper bound from the weighted graph. For comparison, let's see how the usual value iteration is performed in terms of this graph. What we do is, for each state, we update U with the largest weight of outgoing edges from the state under consideration. For example, there are 3 outgoing edges from initial state with their weight 1, 0.6, and 0.6. Then we update U at initial state by propagating the largest weight among them. Here, we see that the value of U has been converged to 1 at the initial state, while reachability probability from the initial state is clearly 0.6. Indeed, this part of the MDP is an end component, which is the source of non-convergence. Our algorithm instead computes the largest width of path to the final state. Here, the width of the path is the minimum weight of constituting edges. For example, the following paths are all paths from initial state to final state, and their widths are all 0.6. In this example, it would be easy to see that the width of a path from initial state to final state is always 0.6, and thus we put 0.6 as the new value of U at the initial state, which is the true reachability probability. In this way, we globally propagate the width of a widest path to the final state, which is not a single edge in general. Notice that the weight of the loop edge is not propagated here. Its effect is suppressed by the edge to the final state. In this way, our method naturally ignores problematic information from end components. Lastly, the width of the widest path can be efficiently computed by the Dijkstra's algorithm. We explained how our algorithm works for MDPs. Here we briefly explain how we handle arbitrary stochastic games. Our algorithm receives a stochastic game and a positive number epsilon, which represent a precision requirement. Starting from canonical lower and upper bound, we update them until their values at the initial state is epsilon close. This structure is the same as any existing BVI algorithm. At each iteration, we update lower bound via the standard value iteration, and then we reduce the stochastic gain into an MDP using the current lower bound as an oracle. This reduction is eventually correct in the sense that for every sufficiently large I, the reduced MDP has the same reachability probability as the original gain. Lastly, we perform our global propagation over this MDP and generate a new upper bound. We proved that by letting the while loop iterate forever, our algorithm generates a decreasing sequence of upper bounds that converges to optimal reachability probability, which means our algorithm always terminates and returns an approximation of V with its error range epsilon. Lastly, we will provide our experimental result. We compared our algorithm with 3 variants of existing algorithm by Kelmendi et al. We tested the algorithms against 13 different stochastic gains generated from 5 models. We observed that our algorithm was fastest in 7 instances out of 13. We also observed our algorithm is stably fast, while every other algorithm is sometimes very slow or fails to finish their computation. As a summary, we introduced a novel algorithm of bounded value iteration, which is faster than the existing one. For future works, we would like to adopt our technique to a general reward setting, as it can only handle reachability objective right now. We would also like to extend applicability of our technique to more complicated systems such as black box bound. So this is the end of my talk. Thank you for your attention.